Hello and welcome back. Today I want us to build a toy version of GPT. So if we recall what we have to build for memorizing transformers, we have XL transformer layers, KNN attention layers, relative position bias, but really the best first step is to build a vanilla decoder model. And what this looks like is a GPT-like block. So we're going to build that today, and then we're going to assemble these blocks, and we're actually just going to make a very quick and dirty model that is like a small version of GPT, and we'll run it through our training pipeline that we built in the last video. So we're going to do that line by line. And then I want to cover a couple important PyTorch topics that will hopefully teach you a few of the ins and outs and prevent you from making any kind of subtle errors. And it'll also help deepen your understanding of both self-attention and how certain aspects of PyTorch work. Okay, let's get started building. So I've imported Torch up here, and now I'm going to introduce a few sample numbers. And we'll use these to keep track of different dimensions, different parameters. And so when we create fake training data, we can watch as it goes through each step of computation in self-attention. So I've got a sequence length, an embedding dimension, head dimension, number of heads, batch size, and a scaling factor. So we'll keep coming back to these, and it's good to just take a glance at these because we're going to come back to, we're going to see these numbers a lot. So if you remember offhand that we have 8 heads, and the sequence length is 512, and the batch size is 16, as we go through, we're going to be checking the shape of what we do constantly. And so if you have a sense of what these numbers are, you'll be able to remember that, that first dimension is 16, it must be the batch size. And the third dimension there is sequence length, that's 512. So this just makes it a little easier because we're going to constantly be checking the shape to make sure we're doing things right. So we're going to start with single head attention, and then we'll build out the batch and the multi-head attention version. So I'm going to create some fake input data. So this will be torch random, which just creates random numbers. That'll be 512, by 300. And now we're going to create query key vector transforms. So let's take a quick look at what we're building here. Here's attention, and it's a function of a query key value vector. And we perform this computation. So we multiply query and key together, we divide by the scaling factor, we apply softmax, then we multiply by value. And I'll go through all of this in great detail. Here's another version, but we're going to stick with this one for now. And as a reminder, this multi-head attention is what we're building here. And this is how it fits into the larger architecture of a transformer decoder block, which is the block here on the right. So it's just one component, but it's somewhat involved, so that's what we'll be building today. Okay, here's key query value transforms. These are linear layers, and then we're going to create query key value data by putting our input data, I have to load this again, by passing our input data through these different linear layers. A great question to have at this point is, what are query key and value? So these terms are actually from database terminology, where, for example, we have a query, and let's call it sunset. So we are looking for pictures of sunsets. So we want to match our text query against some database, and of course these database items that we're interested in are images. And so how do we match text against the values in this case, which are images? Well, each of these images has some metadata, like captions or alt text or something like that. Best sunset views in New York City. So these act as the keys. So the query we put in here, and it matches in similarity against a bunch of keys. In this case, well, it's more complicated for Google search, but pretend it's just matching the alt text and the metadata here. These are the keys, and then the keys are attached to specific pictures. So that's kind of the database overview. Now, I don't really think that analogy is great. I think it's kind of confusing. It's a very loose analogy. So I don't like to over rely on these terms. I don't think they lead to a good understanding. What you can definitely notice here is that these three are just linear transformations of the input. They're literally just three versions of the input data. And they're even randomly initialized. So they don't have inherent structure. They're the same size. They're just linear operations. Now, because of the way they're used in our computation, how they're multiplied, what operations happen between them, when they're incorporated in our computational graph, they end up taking on different roles, and they end up learning different things in much the same way that a large multi-layer vision model, just by the nature of its architecture, learns different things at different layers and is based on different features that we've built in that tell it about how image data should be processed. So we'll see in just a second what each of these parts is doing, what role it plays in self-attention, and then tell a story about what's happening. And I think at the end, the story that I have about what it's doing internally is hopefully a little different from what you've heard before. Okay, on to building. So the first step, let's look back at our equation. Let's tackle this term first. This is the query and keys. So let's verify the shape of our queries. It's 512 sequence length by 256, and we got 256 because it's number of heads times head dimension. But remember, we're just doing single head attention here, so we're not going to split this out. We're just going to keep 256. So all you have to focus on is we have 512 tokens, and each token is a 256 length vector. And the same goes for keys. Remember, these are just, there's nothing special about them. At initialization, they're random. These are just different versions of the input data. We're just making projections of the input data. And then we do some computation with them. So the first thing we have to do is multiply query and key together, but of course, these are different shapes. The inner dimension doesn't match. So we need to transpose the keys. And this gives us 256 by 512. And so now queries are 512 by 256. This inner dimension of 256 matches. So we can create our QK. And we end up with a 512 by 512 dimension matrix. Okay, next up, let's see. It's scaling this QK. So we divide it by the square root of the dimension size of K. And so if you're doing multi-head, that'll be the dimension of the head. But here it's just single head attention, so it's 256. So we're dividing by the square root of 256. So why do we do this? Remember that we're multiplying queries and keys. And when we do this, whenever two large numbers meet, they'll create an even larger number. And when two small numbers meet, they'll start shrinking. And let's remember what we're about to do. We're actually about to pass this whole thing through softmax. So the softmax function will take very extreme values and it'll squash them into either 0 or 1. So if our numbers are kind of well behaved and they're sitting around here, it'll create us a nice distribution. But if all of our numbers are extremely high or extremely low, it's going to squash these into 0 and 1. So the output of this softmax applied to QK would just be 1s and 0s. And this doesn't make for very good learning. We're going to pass this on to the next layer and the next layer, and this kind of skew makes learning very unstable. So the main thing we want to do is preserve variance, and that's what scaling does. So let's implement our scaling, and then I'll give you a quick example here. So we're dividing qk by the square root of the dimension. Let's take a look at a random matrix, rather a random set of matrices here. So I have these very large matrices, and I'm going to multiply them together. They're random. The variance of one of them is 1, and that's just by nature of how randn works. It creates a matrix with variance 1. But what is the variance of AB? That is, 2 of these matrices, each with variance 1. What's the variance of their multiplication? It's 269. So with that, we have this gigantic variance, which is what we don't want. What we can do now is exactly what we're doing with qk. Let's divide AB by the square root of the dimension and see what the variance is. As you see, it comes back to 1. And this really works for any size dimension. We have variance 1, it blows up to 16, and then it comes back down to 1 after we divide it. So this is just a way of ensuring that our variance stays at 1. Now you might notice that the magnitudes here actually change quite a lot. So even though, let's say, this is bigger, even though our variance has been brought back to 1, the magnitude of this is much bigger than the original magnitude. So these original matrices had norm as just a way of getting the magnitude of 358, and their multiplication has 801, even after we divide it by the square root of the dimension. So the norm is still really big, even though the variance is 1. So does it matter that this norm has kind of exploded? Let's remember what we do in softmax. We have the equation here. And let's take a look at a couple examples. So I'm just going to create a fake set of 4 data points here. This ranges from 1 to 100. So this is a very, very large variance. And when we run softmax, we get the last value basically having 1, and everything else is squashed down to 0. So this is a bad example. Let's get another set of data with a little more even values. Oops. And now we see we have much better softmax values because the variance between these, it ranges from 1 down to 0.7 up to 1.2. These actually stay pretty well ordered. But what if we increase the norm of this? So the variance is pretty good, but let's increase the norm. In fact, let's just add 1,000 to each data point. What happens to the softmax? The softmax stays exactly the same. And that's just by nature of how the function works. So we really care about variance. It's okay if the norm explodes. This is just a little demonstration to show why we're scaling this down. Now, I want to create a little fake data that's even faker than the fake data we're using, just as a demonstration so we can actually watch what's happening inside of the query key matrix. So I just made up some data, but it's very small and very interpretable. And we can graph it. So that's what we'll do. I've just created a little plotting function that I had much help from ChatGPT with. Thank you, ChatGPT. Configuring these plots is sometimes very tedious and hard, but it did a great job here. Let's take a look inside of our QK, our query key, also called our attention scores. So what's happened here? We've multiplied one projection of the input against another projection of the input. So we've multiplied the queries by the keys. Now, at first when the model is initialized, These attention scores won't really have a pattern because it's just going to be random scores. But as the model trains, we'll see examples like this one. So what's going on is that the model has learned to alter the query and key matrices through backprop, such that tokens that are similar or related or have some interest in one another in some way will have high scores between the query and key matrices. So let's take dog and animal in this sentence. The query and key matrices will see dog and animal as the input tokens, and remember this is in our trained network, and the matrices will project them closer to one another than they will to the other tokens. So when they're multiplied together as keys and queries, the resulting multiplication score, the attention score, will be high. And that's what's happening here. Similarly, if words are not similar or related, the scores should remain low. Now, this isn't just semantic. So similarity like dog and animal are obvious, but it ends up occurring for all kinds of relationship, especially in large complex models. So if words are, for example, syntactically related in the way that a is the article for dog and an is the article for animal, then there's some interesting information there and some interesting relation going on there. And the model ends up trying to maximize those scores. And you see this in all kinds of complex ways, like pronouns having very strong attention scores with the name of a person that they modify or represent, even if it's on the other side of the sentence. So our attention scores are particularly inside of different attention heads. You get these really interesting relationships of how words have decided to pay attention to one another. And again, this deciding is just a result of the model structured the way it is, and we backprop it, and our goal is to optimize language modeling. Lastly, notice that these attention scores are not symmetric, and that is on purpose. That is, this is right here might find dog very important, and it might find animal very important, but it's not necessary that dog finds is very important. So each token gets to choose how interested it is in all the other tokens, independent of how interested all the other tokens are in it. Okay, something we need to add in here that's not in the equation is the causal mask. So this is a decoder model, meaning that we want the model to look at a string of text and predict the next word. So we have our original sequence, a dog is an animal, and what we do with self-attention is actually create 5 distinct training tasks out of this one sentence in parallel. So we want to feed in a and get dog, and then we want to feed in the sequence a dog and get is, and we want to feed in the sequence a dog is and get animal, and so on. So, for example, in our 512 token length sequence, we're actually creating 512 examples out of that one sentence. This is a nice trick that lets us feed in everything in parallel. But the only thing we have to do here is to mask out or erase for each of these examples any words that will be in the future. So what do I mean by that? Right now, every token gets to attend to every other token. And if we were using an encoder model like BERT, that's a desired behavior. But this is a decoder model, and we don't want a token to see the token it's trying to predict or future tokens that could tell it about the future token it's trying to predict. So you wouldn't want, if we feed in a dog, we don't want it to see any of these remaining 3 words is an animal. You don't want it to see is, you don't want it to see animal. So what we're doing is we're treating each of these rows as an example. And what we want to do is erase this upper triangle here, setting these values to 0, so that even though there's information now about, for example, how A attends to animal, animal, according to A, comes way in the future. So we set all of these to 0. Actually, this is already 0, so that's a bad example. But A, for example, attends to Anne. We want to set all of these to 0. We don't want A to see anything in the future. And so we set these not technically to 0, but we set them to negative infinity. And that's because we're going to feed it through softmax, and softmax will take anything that's very, very small, and it'll turn into 0 for us. So we want to turn all of these upper triangle values very small, feed them into softmax, and the result is that these will all turn into 0. Let's do that now. We're going to create a mask. So I'm going to call torch ones, and this function just creates a tensor of ones of any shape that you like. And here we're just going to make a 5 by 5 tensor. But instead of ones, I'm going to change the d type to bool. So we won't get ones, we're going to get true instead. So we have a tensor of trues. Now, there's another handy function here, which is triangle upper. And there's an associated triangle lower. But basically, these take your matrix and they pick out the upper triangle. And this one here is specifying, well, along which diagonal do you want to make a triangle? So I'll show you what this looks like. It's doing what we want, where we're setting all of these values to true, and eventually we're going to mask them out. But if you wanted, this is the parameter that controls where along this diagonal we actually start applying the mask. So it could be 2, and you see now that the true doesn't start until here. So this just controls which diagonal we're on. We're going to keep it at 1 because we want the first token to see itself and nothing else. The second token to see itself and the previous token, but nothing in the future. The third example will see the first 3 tokens, but it won't see the 4th and 5th, and so on. Okay, now let's apply this to our toy query key values. So this function will actually apply this as we like. So this is called masked fill, and it's kind of a logical operator. So it's saying apply the mask, and wherever mask is true, apply this value. So conditional on where mask is true, applied to toy QK, apply this value. What we end up with is our QK, but these values have been set to negative infinity, which is just what we wanted. Now let's plot this. Let's take a look at this. Great. It's the same thing, but these upper triangle values have been set to negative infinity. Okay, the last step is to apply softmax. And we can do that just by calling torch functional softmax and passing in our toy QK masked, which is this. And remember that softmax is going to take all of the values by row, and it's going to redistribute them with a sum of 1. So let's see what that looks like. Negative infinities have all been turned into 0. Negative infinity, by the way, is not the concept negative infinity. It's just a very small number. But it gets squashed into 0. And for each of these rows, the remaining values have been redistributed such that they sum up to 1. So this first value, 0.9, well, there's only one value, so all of the weight here is going to be 1. And we'll refer to these as weights. So it's kind of creating a weighted distribution that sums up to 1 for each of the tokens for each of our examples. Similarly for dog, this was added up to 2.6 with 0.6 here and 2 here, and it redistributes it this way according to softmax. So this is just what happens when you apply these 2 values and you pass them through a softmax. Similarly for all the rows. So these are the softmax masked attention scores. Okay, so what do we want to do with this? We have these 2 projections of our input. They come together, and basically, if any 2 tokens in the query input version and the key input version, if they have high similar values along the same dimensions, then they get a high corresponding score. And we interpret this as basically interest in different tokens. So dog is interested in dog and a bit in A. Animal is interested in animal and in dog. What do we do with this? These basically serve as weights, which we will use to selectively pick out the values. So let's look at the last row here, corresponding to the animal token. When we multiply this vector with the values matrix, the magnitude of these attention scores is how much weight we will give to each of the value vectors in the value matrix. Here are these values again. They've been rounded to fit in here. And here's basically what we're going to do. We'll say that we have some vector corresponding to A, and these are the value vectors. One corresponding to dog, to is, to an, to animal. And when we do the matrix multiplication, we're just taking a weighted sum of these. So the animal output vector, if you pull it out from the final query key value matrix, this is just going to be a weighted sum of the other tokens. So it'll take a little bit from A, a lot from dog, 0.46 from animal. And so this final representation has basically got to see all of the other tokens in the sequence. The attention scores are just there to give us a method to weigh how much each example should attend to every other value in the token matrix. That was the goal. So what happened? Our animal vector came in on its own, and by the time it got to the output of query key value, by the time it got to the end of single head attention, it incorporated information about other tokens in the sequence. It is attended to the other words. Okay, let's finish applying this to our original query key values. Let's remember we have our QK and we've scaled it. So we're going to apply the exact same functions. We're going to create a mask and create a QK masked. We can see negative infinity is set along that diagonal. And then we're going to do the softmax of this masked version. And these turn into zeros. And all of these rows are now summing to 1. So across these 512 tokens, it always sums to 1. Now we have the values, and what's the last step here? We just need to multiply this term by the values. So let's go ahead and do that. Let's remember what shape each of these are in. 512, 512. Values is 512 by 256, so the inner dimensions match. So let's go ahead and compute QKV. And there we go. We've completed a single head attention pass of some fake data. Okay, let's step back a bit. What is the story that we end up with? After training for a while, attention behaves like so. The query projection has some information about the tokens. The key projection has some information about the surrounding tokens. And we multiply the query and key to get these kind of high affinities where the tokens match. And then we use these affinities, these attention scores, which I think are well named, to weigh the value vectors, which actually contain the information that gets passed on to the next layer. So let's revisit the query key value database analogy. Is this a perfect analogy? No, not really. It's a loose analogy. What can we say for certain? The matrices are initialized randomly, so they're not really imbued with this kind of query key value role. But there is some structure in the attention mechanism itself, in the architecture. So we've built in some inductive biases into how the model should process data. So it does allow each token vector to communicate with every other token vector. It does provide a way for each token vector to weigh how much it communicates with the other token vectors, and it does provide different representation spaces for the same input. And lastly, it does have a value representation that is primarily going to pass itself into the output, more so than the query and key, because they go through a softmax, so a lot of the information gets lost. I think a key point here is that if you train the model, these components learn to take on roles through backprop, because the model has to use this structure that we've given it, and it has to maximize its objective of learning language. So we have built in certain inductive biases about what we know about the data, namely it's a sequence of texts. Assumptions about the meaning of the data, namely that a word's meaning is based on the words surrounding it, and in this case, the words preceding it, because we're not allowed to look into the future. Assumptions about how data should interact with itself, so we provide the ability for each word to communicate with every other word in the sequence, not just a small window or the nearest few. And so on. There are all kinds of inductive biases that we've built into the structure of the model and the way the data is handled. And this applies to all models, to CNNs, to RNNs, diffusion models, random forest, anything you can think of. So while the database analogy doesn't hold strictly, you can say that because of the way we've structured the model, the data, in some sense, self-attention does end up manifesting as this kind of query key value matrix, roughly taking on the database role. So you can actually go and inspect a fully trained model and see, it's doing a good job here of making sure two related words have similar representations. The key and query matrices are doing their job, so we get this high similarity score, and we end up retrieving the right value vectors. Now, it's sometimes useful to use these analogies, or to anthropomorphize the model, meaning to attribute to it human characteristics, like saying the model wants X, or the model sees X, or the model is trying to do X. I think this talk is actually a very useful way to understand, or remember, or mentally model what's going on. It is a good tool, but you should also verify that you can talk about the model's computation in much more objective and specific set of terms. So over-reliance on anthropomorphizing or on using this kind of query key value analogy can lead you down the wrong path into thinking that the model needs or wants something that it doesn't really. And you'll waste your time pursuing bad lines of research or debugging things that don't exist. There are some other very good questions to ask about self-attention. So, for example, why this specific set and configuration of components rather than some other? So, you could imagine having, for example, the same scheme here, but instead of a value matrix, we just double the query matrix and put it here. Or maybe you have some other matrix that you put somewhere else in here, and you have a different operation. So there's all kinds of these variations you can come up with. So what's so special about this architecture specifically? Why is transformer used everywhere for the last 7 years? So there's actually a lot of history about why this looks the way it does specifically. So there are different kinds of attention mechanisms dating back a few years. There are different ways to incorporate it. So there's a gradual progression to this version of self-attention. But the early form of attention was actually a way to remedy the fact that sequence-to-sequence networks and recurrent networks would forget their original inputs over long sequences. So attention provided during these recurrent computations weighted connections back to the original input, so you could remember long ago what the recurrent relation has forgot, or the hidden states have forgotten. And the title "Attention is all you need" some years later is basically saying, let's drop all the other stuff and make this somewhat minor component called attention and just make an entire network out of attention. You can read more about the history here, and this is an excellent blog that covers both the history and the different variations. And in general, this is a great blog for kind of any topic, so I encourage you to look through the archive and find something that interests you, because she provides great primers. So I think I've mentioned this blog before, but a great resource. The other answer I'll provide to why we use this version of attention is simply that it works. Because it works is actually a very good reason. So empirical verification is very important in modern deep learning. So I'll contrast this with the idea that you can sometimes have a very good reason or a very good story about why an architecture should work well, or why some new idea should work well, but it just doesn't. And sometimes something works really well, but you have no real explanation for why it does better than the alternatives. So it's good to develop your understanding and have ideas about why things are or aren't working, and have some story about what a model is doing so that you can maybe address certain drawbacks that the model has, but be a little cautious about these kinds of stories of why a thing will or won't work, and recognize that some things work well and there's not a clear explanation why. You can speculate why it does or doesn't work well, but it's not always clear. A great example of this is from the Swiggloo paper a couple years ago out of Google. And this basically outlines new nonlinear activation functions that work well, and they're used today, and they just work a little bit better than the other variations. And if you look in the paper, the author concludes, the new variants seem to produce better perplexities. These architectures are simple to implement and have no apparent computational drawbacks. So for the same computational budget, they're working just as well. We offer no explanation as to why these architectures seem to work. We attribute their success, as all else, to divine benevolence. So here's an author saying, I don't have a great story about why this works better than the alternative, but it does work, and that's what's important. Similarly, there's something called multi-query and group query attention. And I think if you would spell this architecture out, which is, we'll get to multi-head attention soon, but the idea is instead of having the same amount of heads for queries, keys and values, you can actually reduce the number of heads that you have for keys and values. So you're reducing the parameters by quite a lot. And I think if you asked a lot of people before testing this, you could have very convincing reasons and very convincing stories about why it doesn't work well. And yet it works pretty well. You can sort of vastly reduce the number of heads you have, so reduce the number of parameters inside of self-attention. And the resulting performance doesn't really take that much of a hit. So this is an example of something where you have very good reasons for why it wouldn't work, and it does. Or maybe you talk to someone else and they have very good reasons for why it would work, but again, empirical verification is what we care about. I think this is nicely summarized in a tweet I saw recently from Francois Fleuret. Reality telling me if my good idea, for which I have a series of very strong arguments, is actually good. No. So sometimes you have a very good idea and you think this architecture has got to work better. I have all of these justifications, all of these reasons. It often is the case that you go and test it and it's worse or the same, or it makes no difference. I'll leave you with one last thought, and that's in the last couple of years, it's looked like architecture is maybe less important than we thought. So if you're asking why this specific architecture, there might not be anything special. So if you look at research coming out today, there's increasing evidence and a line of thinking that model capability really just scales with compute and data. So as we keep making models larger, training them longer with more flops, and adding more data, they increase in capability predictably. The architecture maybe isn't so crucial. So you could have multiple different architectures, and as long as they pass the threshold of allowing you to scale, are relatively stable to train, then that's all they need to do. So they might be more or less efficient in using this compute, but they are all capable of scaling and increasing their capability. So by that line of thinking, there's nothing special about self-attention. It's just one of many candidate architectures that can work well, and it happens to be very reliable and very efficient, and that is why it is repeatedly used. And there's a nice summary of this idea here from an engineer at OpenAI. He's saying that I train a lot of different models, and you can read this, it's very short, but I'm going to summarize a very short article anyways. Trained on the same data set long enough, pretty much every model with enough weights and training time converges to the same point. So diffusion, conv unets produce the same images as vision and transformer generators. Error sampling produces the same images as diffusion. It implies that model behavior is not determined by architecture, hyperparameters, or optimizer choices. It's determined by data set and compute. Everything else is a means to efficiently deliver compute to approximating the data set. Okay, let's continue. It's time to do the same thing, but we're going to do multibatch and multi-head attention. Now, multi-batch just means we compute this efficiently. We package a number of different input sentences at the same time. And really, it doesn't change our computation much at all, except that the leading dimension will always be the batch dimension. And this just says, for example, we have 16 batches of this, and so we're doing it 16 times in parallel. But it doesn't really affect anything that we build. Multi-head does. So it means instead of doing this one 256 dimension self-attention, we're going to split this out. So we take this long vector and we split it into heads. So each head gets a different chunk of each of these vectors. And we do computation on these slices in parallel. So we're going to do 8 tiny versions of attention, each on different slices of the input vectors. So we'll see what this looks like in a second. Again, I'm going to pull up the sample data just so we can take another look at it. So we're going to have 8 heads, and the incoming vector will be 8 times 32, so 256. And then we're going to split it out into 8 heads of 32 dimensions each. So 256 length vector split into 8 chunks, 8 slices of 32 dimensions. In the same way, we're going to create fake training data. And this time the only difference, see, is that we have a 16 here. So we're doing this 16 times in parallel. Once again, we're going to initialize these, and they're exactly the same. Notice we don't have to put batch dimension inside. So these linear matrices are 2 dimensions, and they operate on the last 2 dimensions of our input data. So our input data could be 10 dimensions long. It could be a tensor with 10 dimensions, and it will still only operate on these last 2. So the last 2 is what we need to pay attention to. And we'll see that when we pass our input data into these will all be the same shape, but they're 16 batches of 512 tokens. And now these tokens have been projected. We have these 3 projections. They're all 256 vector dimension. So here's where we diverge a little. For single head attention, we just went ahead and started multiplying queries and keys. But here we have to split out this 256 dimension into 8 32 dimension slices. So how do we do that? We're going to take each of these, and this is the same code for each one, and reshape it. So this is going to be reshaped according to the dimensions we specify here. So remember, this is 16. The first dimension stays the same. Sequence length is 512. That stays the same. And the number of heads and head dimension actually gets split out. So this 256 becomes 8 by 32. So we've turned all of these into this shape. Reshape is a way to keep the data in the same order. We're just changing the grouping. So we're literally changing the shape of the tensor, but it's the same data in the same order. For example, if we just have a vector that is, this just creates a range of 100. So it creates a tensor that's 100 elements, 0 to 99. And then we reshape it. It stays in the same order. So at the end of the first dimension here, we have 19, and then we go on to 20, and so on. So we've just taken this one long vector here and reshaped how it's formatted. Okay, time to create the QK. So just like we did before, let's remind ourselves of the shape of the K. So once again, we have to transpose K. But first, there's actually something we need to do. So if we performed attention like this, we would be performing 8 by 32, and that's not what we want. We want each of the 512 tokens in the queries and each of the 512 tokens in the keys to attend against each other. And we want to do this 8 times. So what we have to do is actually change the dimension here. And so we're going to transpose, for example, Q. Now what we've done is created 16 batches of 8 heads. So we have 16 batches of 8 groups of 512 by 32 matrices. And so we have, instead of 512 groups of 256 matrices, we have these 8 groups of slices of that original vector. So we've sliced that original long vector into 8 groups, and we bring that dimension out here. And this allows us to compute these smaller vectors against one another for all 512 tokens of the queries and keys. And so for k, we have to do the exact same thing. I'll cover this in more detail, but you should know that reshape and transpose fundamentally do different things, so they're not interchangeable. So you often want to change the shape of your tensors. And view, reshape, transpose, there are many more. These aren't all interchangeable. They do different things. So it's important to know which one does what. And I'll actually cover this later, so you know what's going on. But just to demonstrate that reshape and transpose, even though you come out with the same shape, they fundamentally change how the data is ordered. So I'll take the same example, and when we reshape this 100, we get 5 by 20. And we can go ahead and reshape that again into 20 by 5. In both cases, the order of the data is preserved. We go from 0 to 100. Now, if I transpose the vector, I'll still come out with a 20 by 5 shape, but the ordering of this data is fundamentally very different. So here we're getting the 0, 20, 40, 60, 80. Whereas here we had 0, 1, 2, 3, 4, 5. So if you're not familiar with transpose, you should definitely look that up and get some more linear algebra background here. But essentially what it does is it flips the matrix along the diagonal. So if you took this and you transposed it back, you can see that it would flip to what we have up here. So it's important to understand the difference between reshape, transpose, view, all of these different tensor operations. Okay, we're not quite ready to make the QK, the query key attention scores. We have to once again transpose K so that the inner dimensions match here. We want to multiply 32-dimensional token vectors by 32-dimensional token vectors. So one more time, we have to transpose K. And here, -1 and -2 just mean you start counting from the other direction. So 1 and 2 refer to 1 and 2. And this is the 0th dimension, but these can also alternatively loop around negatively. So this is -1, this is -2, this is -3. Okay, so now our K is in this shape, and our query is in this shape. So remember, just look at the trailing 2 dimensions, 512 by 32, 32 by 512. So we can multiply these together. So let's do that. We end up with 16 batches of 8 heads, and these have each computed their own version of attention. Now, once again, we apply the scaling factor, and instead of writing it out, I've put it up here, head dimension times -0.5, which is the same as 1 over the square root. So multiplied by the scaling factor. And once again, there's nothing different in what we did before. We're applying the mask and we're applying softmax. So we've now completed everything here in our equation except for multiplying by the values. Let's remind ourselves of the value shape. This is 16 by 512 by 8 by 32. Just as we did for the others, we want to pull the head dimension out of the matrix multiplication. So we don't want it to be in the trailing 2 dimensions. So we've now created 16 batches of 8 heads, 512 by 32. We can now multiply QK and V together. And we end up with 16 by 8 by 512 by 32. Remember, the 32 came from the values matrix here. So now we have to recombine the heads. So we have 8 mini attentions operating in parallel across 16 batches. So now what? What we do is we concatenate them before we put them through an output matrix and pass them on to the next layer. So we do this by transposing the head dimension back to where it was originally, and then we recombine it with our dimension vector. So we're going to end up with 16 by 512 by 256 again. So let's first bring the head dimension back next to our head dimension size. And now we can actually just reshape this, and these will all concatenate into one 256 length vector in just the same way that it was 256, and we reshaped it by splitting it out into 8 versions. This will literally just concatenate it. And then we feed it through an output layer, so all of this information gets mixed in the output layer. We have the end of our multi-headed self-attention. We need to pass it on to the next layer. So we just have a linear layer that I will call output matrix. And it matches this dimension against the embedding dimension. So remember, our embedding dimension was 300. So inside of our architecture, we'll have the multi-head attention and then an output layer. And this output layer, where it's 300 dimension, matching the embedding dimension, this will go through add a norm and feed forward more and more layers until eventually at the end, we have this output that is a 300 dimensional embedding. And that's how we can pass it through a final layer of embedding that maps the 300 dimensional embedding onto our vocabulary size. And that'll be an output layer, and that goes through softmax, and then we predict loss. So that's just what the output matrix is doing here. We're reconverting it to a different shape and mixing all of those concatenated heads together. And so this is the same shape of data that we actually entered with. And it's the same shape that we want to leave with. So our fake input data was 16 batches of 512 length sequences of 300 dimensions each. And that's what we come out with at the end. Now, I promised you at the beginning that we would actually make a GPT-like model, a toy GPT model. So I'm going to go ahead and do that. So what do we need to do? First, let's wrap this self-attention, multi-head self-attention, let's wrap it into one class. So I've already built this. And you can look through this yourself, but there's nothing special going on. We've covered each and every line here. And this is just putting it all together. You want to make sure all of your parameters and layers are initialized up here and not in the forward pass or somewhere else, because it won't be the same parameters. Each time they'll get initialized anew. So you want to make sure that they're initialized once and then trained successively. You don't want to reinitialize any parameters. And I think Torch will warn you if you do so. All we're passing in is the input data, and the batch size and sequence length are agnostic here. This multi-head attention can take any batch size, any sequence length. All it requires is that we specify the embedding dimension, because we need to know that in order to split this out into heads and head dimensions. But yeah, there's nothing new here. We're just following all the steps that I just walked through, and we return an output. And we're going to skip relative positions or any position embedding whatsoever. So right now, multi-head self-attention has no sense of where these words are in sequence. There's no sense of order, but we'll build that in later, and we've got a to-do here. So just to make a fake batch and call our class and see that it works. I've created some fake data, and we're going to make a multi-head attention class, initialize it, and then pass through the forward pass. You don't need to call forward if you just call the class, and it's a torch module, which is another important thing to note when building torch components or models. It understands that if you just call the class, it's calling forward pass. And so we get out the data size that we wanted. So it's doing something, and hopefully it's doing the right thing. What we can actually do is, if you remember from the last episode, we built our whole training pipeline, and I've got this ready to go. And I've added in multi-head attention here. And remember, this is our old model. This is our old model that we completely made up. it doesn't really do anything. What we can do is create a similar version, but this time it's with our multi-head attention. So I'm just going to define a layer, and each of these blocks is the same. But this is just roughly following what's going on here. So we have multi-head attention on the right side. This is the decoder. Multi-head attention, normalization, feed forward, normalization, more multi-head attention, and eventually we have a linear and loss function. So you'll notice there's no residual connections here just because I want to make this very simple and very brief, and sequential doesn't really support this in any kind of nice way. But we do have these basic GPT-like attention blocks followed by feed-forward layers. So we've crossed out this model, and now we've got GPT Mini. And we can run this, and it has quite a few more parameters, so I think it'll take a while. But we just want to see that it creates a loss, which is great. So we've managed in a very short amount of time, relatively, to build an entire GPT model, line by line. And later, of course, I'll talk through a little more about what we're doing in these feed-forward layers, but really the point is that we've created multi-head attention. We've passed some data through. This is real data from our archive dataset. And it follows some feed-forward nonlinearities, but we're doing layers of multi-head attention. And this is very similar to what happens inside of a GPT decoder model. And the loss is decreasing, so great. Okay, one PyTorch thing I want to clarify is the different operations or the different names we have for multiplying something. So this is a little confusing when you first run into it because there's actually all of these different ways of multiplying two tensors together. I've just written out here the differences and what they do. So mul is element-wise multiplication, and that's Hadamard, and that just takes two tensors of the same size and kind of lays them on top of each other and multiplies each element by each element. Dot is reserved for the product of two 1D tensors. Matrix multiplication is two 2D tensors. BMM is batch matrix multiplication, and this is for 3D matrices. And torch-matmul is a general matrix multiplication for tensors of any size. Depending on the inputs, it will perform dot, matmul, BMM. So this is kind of the general one you use. And at is actually kind of this funny one where it's the same as matmul. And if you look at Python documentation, the at operator is intended to be used for matrix multiplication. No built-in Python types implement this operator. So it's inside of Python, but it doesn't operate on any built-in Python types. It operates on NumPy and Torch and other kind of tensor libraries. So these are the differences in the different kinds of multiplication you do. Typically, we just do at because it stands for matmul, and it's the most general one. You'll notice inside of each of these description, I've put whether or not this operation broadcasts. Broadcasts, no broadcasting, does not broadcast. So what is broadcasting? It's a very important PyTorch thing. So two tensors are broadcastable if the following rules hold. And you can look up this page for both Python, or rather PyTorch and NumPy, and it explains broadcasting. But briefly, this allows you to take two tensors and say they're not the same size, but there's some kind of intuitive understanding of what you want to do. So you have some matrix and you want to add 1 to each of the values. Well, can you just say my matrix plus 1? Or do you have to create an entire matrix that's the exact same shape of 1s and then add it? So broadcasting is an example of the addition operation broadcasts, meaning PyTorch will infer for you because addition broadcasts that what you actually want to do is expand that 1 out into the same size as your tensor and add them on top of each other. And so every operation in PyTorch either broadcasts or it doesn't. Here are the rules for broadcasting. Two tensors are broadcastable if the following rules hold. Each tensor has at least one dimension. Okay. When iterating over the dimension sizes, starting at the trailing dimension, meaning the last one, the dimension sizes must either be equal, one of them is 1, or one of them does not exist. That's starting at the trailing. So the best way to do this is actually play with a bunch of examples. And again, if you go to these web pages, they'll give you examples, and I'm sure you can find more YouTube videos that cover broadcasting. The reason I mention it is that if you're not aware of what operations broadcast and what don't, you might be making subtle mistakes under the hood. So just to demonstrate broadcasting in action, will these two broadcast? Well, the inner dimensions match here, and we're going to matmul them, so that's okay. Each of these dimensions, starting at the trailing dimension, the dimension sizes must be equal. One of them is 1, or one of them does not exist. So in every case where they don't match, it's a 1, it's a 1, it's a 1. So this should work. And each tensor has at least one dimension. That should be obvious. And so it automatically broadcasts, or it kind of copies out. For example, this one, it copies it out 10 times in this dimension, and it copies B out 64 times in this dimension, and so on. So because this operation of matmul broadcasts, it makes these assumptions about what you wanted to do, and then fills it in for you. What about these? Will this broadcast? Well, let's check our rules again. Each tensor has at least one dimension. The operation broadcasts. And when iterating over the dimension sizes, starting at the last one, the sizes are equal, one of them is 1, or one of them does not exist. So it's a little tricky to see, but if you go through it, you can tell, okay, well, the inner dimensions match, so matmul will work. And then we have a 1 here, but we have an 8 here, so this dimension is 1, and that's okay. But before this, there's nothing. But that's okay. If the dimension does not exist, it's just going to fill that in. So it's actually going to, under the hood, add a 1 and a 64 and an 1152 in front of B. So it's going to create copies of this many times. And you end up with 1 by 64 by 1152 by 1 by 16. Broadcasting helps us in this way, in that it's kind of a good abbreviation. So otherwise we would have to do things like, for example, here we would have to tile and expand and copy, and we'd actually have to perform a lot under the hood just to get what we want out of it. So as an example, let's say we want to add two tensors together. Here's an example of where broadcasting helps. So without broadcasting, and I'm going to do it the without broadcasting way, we want to add A and B. And so A is just 0, 1, 2, 3. And B is this big tensor of 1s. And so if we wanted to add these and we couldn't broadcast, we would first have to expand A out so that it matches the dimensionality of B. So what we've done is A expanded turns into this. So we had to do an extra operation here explicitly, and this can make our code very messy. And eventually it gives us the answer that we want. When in fact, because addition broadcasts, this just happens automatically. It's inferring what we want to do and making it happen. However, you have to be careful because PyTorch is making assumptions about what you want to do. And so if you're not very clear about what's going on and how PyTorch works, you can do something and PyTorch thinks it's helping you because it's making an assumption about what you want, even though that's not what you wanted. So instead of throwing an error, it will automatically reshape your tensors and perform the operation, even though maybe what you wanted is PyTorch to say, your tensors don't match, I'm not going to perform an operation, and that would allow you to debug it and say, oh, actually, I thought it was a different size, I have to go and change something. So an example here happens in the loss function, and you can read this. Will this work? Yeah. You can go and read this in the forums, and the forums is full of problems like this, where, for example, someone assumes that this loss is going to work one way, and it doesn't. And there's actually a bunch of people complaining, and eventually they even fix this to say it will broadcast, so the operation broadcast, but this was such a common occurrence that they added a user warning to say your target size and input size are different. So I'm just going to warn you, I'm still doing the operation, but this will likely lead to incorrect results due to broadcasting. Please ensure they have the same size. So this is where they've been kind enough to add a warning and say, I'm doing the operation, and I hope this is what you wanted. So this is just an example where broadcasting hurts. This is why it's important to understand the rules of broadcasting and what operations broadcast and what don't. Okay, I want to talk a little bit about multi-dimensional matrix multiplication. So if you're already familiar with this, great, you can skip this section, but if you haven't encountered this, you might be a little confused about how multi-dimensional matrix multiplication works. The important thing is to recognize that the last two dimensions are the ones being multiplied. All the dimensions that come before the last two are basically saying n groups of m groups of k groups of this final two-dimensional matrix. So the best way is to play with some examples. So let's say we're multiplying these two three-dimensional tensors. A looks like this, and B looks like this. And I've made them this way so that you can actually just do the math in your head and see what the results are. We have these batches of 2x2 matrices. And the result is that the first batch multiplies against the first batch and doesn't interfere with the others. And likewise for the others. So that the second batch multiplies by the second batch, the third by the third. So first row by first column, so that's 3 times 6 plus 3 times 6. And that will be the same value in all of the results. So we get 18 plus 18 in all of these. And similarly for the other batches. So it's recognizing that batching just groups our 2x2 matrices. When we do matrix multiplication, we're just grouping our 2x2 matrices in different ways. If you have four-dimensional tensors, it works exactly the same, but it helps to look at examples, I think, always, and really solidify your understanding. So let's take a look at A and B. And here we have four groups of three groups of 2x2s. So 1, 2, 3, 4 groups of three groups of 2x2s. And if you do the matrix multiplication, you'll see the exact same thing is happening. That the 7 by 3, so the first group of the first group is just this top matrix here. So we're doing 7s by 3s, and that makes 21 plus 21 in each of our elements, so we have 42 in each of these. This gets copied here. So this is just a way to make sure that you're understanding what's going on. Lastly, because we do so much of this kind of reshaping and shuffling of data inside of multi-head attention, I've gone completely overkill and given you some examples where we have this initial data, and I'm going to keep reducing the dimensions or expanding the dimensions or reshaping it. And you can see, so I have A and C as my matrices, and they always start out this way, and I always end up reshaping them in some new weird way. But in all cases, because the last two dimensions are preserved, this 3 and 5, we always end up with the same answers. And you can read through this on your own. But essentially, no matter how I'm moving around and shaping these large 5 up to 6-dimensional tensors, I'm always getting the same answers. Except for this last version. And why is that? It's because in example E, I've created 96 by 5 matrices. So in all of these, I'm preserving the 3 by 5 by 5 by 3. Here, I've actually changed the dimensions of the last two 3x5s, and that's why this one doesn't work. And you can verify by using torch all close, and this will confirm for you that if we flatten all of these results out, the data shape is the same. Rather, the amount of elements is the same. The data was initialized the same, and even though we've reshaped it in all these different ways, the result of A and the result of B are the same. And likewise, result of A and C are the same, and D and E is not the same. It's not even the same shape. So this is just an overkill way, and you can play with this example, of making sure that you understand how these potentially very large dimensional batch multiplications work. I also want to give a kind of general warning to pay attention to what your operations are doing. So I mentioned earlier that reshaping and transposing, or permuting, for example, they can all reshape your data into the size you want, but they're fundamentally rearranging the data in different ways. And it's important to observe this. And so I'm just going to include a couple examples and a couple tips here that will make you aware that these operations perform different things. So let's, for example, create a tensor that is just 0 through 23. View is a way of keeping the underlying data the same and rearranging the shape. Transposing, for example, is another way of rearranging the data. So I'm going to take this new view that I have of A and transpose it. What happens now if I try and create a new view of this transpose data? So I want to keep the data the same, but I just want to rearrange how I view it. I want to rearrange the shape. This doesn't work. It didn't work, and that's because when I transposed the data, I made the data non-contiguous in memory. And so at this point, certain operations are not allowed. We can verify that A transpose is no longer contiguous. But what happens if I try and do the exact same thing, but instead of viewing, I'm going to use reshape? They seem like kind of the same operation, right? Here it actually works. So what's going on here? View basically will not let you change the shape of a tensor that is no longer contiguous, whereas reshape has a different kind of property on the back end. If the data is contiguous, it'll basically just call a version of view. But if the data is not contiguous, meaning it's been shifted around, reshape will actually just make a copy. It'll make a completely new set of data. Whereas with view, we're always dealing with the same exact set of data. And we can actually see in memory the location of these different tensors. So our original A is located here, and our transpose version is even in the same location. But this reshape was actually a copy. It didn't operate on the same data. It made a copy because it couldn't operate on this data as a view. So it made a copy and then reshaped it. And so it's at a different address. It's different data. So it's important to recognize if you think you're modifying the original underlying data, you're actually working with a copy. And so there are all these kind of subtleties about what these different operations do, whether or not they make a copy, whether or not they preserve contiguity. So it's important to be careful with these. And don't just, if you want to change the shape, use all of these interchangeably. Have a very specific, concrete idea of what each of these operations does and stick to that. Okay, the last thing I want to do is go through an example of multihead attention. When the first time you see this, there's a lot of reshaping and transposing and moving data around, and it can be a little unclear where exactly your original data is going. And you might be unconvinced that it's actually doing what it's supposed to do, whereas the heads aren't interfering. You're actually getting a slice of the vector and you're performing attention these multiple times. So in another bit of overkill, we're going to go through a multi-head attention example using very, very tiny vectors with integers so that we can actually keep track of what's going on at each stage. So we're going to get a very solid grasp with a very simple example. Okay, so here is our query data. And this is I'm going to use this convention for naming the dimensions. T is sequence length. OD is original dimension of the token. H is the number of heads, and HD is head dimension. And so I'm going to go through this, and it might suit you better to walk through it on your own a little more slowly, but I'm going to walk through it here. So we have these 5 examples of 8-dimensional data. So these will be 5 tokens, and these 5 tokens have 8 dimensions, and this is our query projection. And now we're going to split this into 4 computation heads, so 4 heads that are 2-dimensional each. So we've taken this one long dimension, and we've taken these 2-dimensional slices out of this 8-dimensional vector, and we've lined them up like this. So these are still individual tokens, but we've just sliced the dimension into 4 heads. But now we're going to do the transpose. So we're going to make heads number of groups for attention. So we're going to make 4 groups for attention. And each head is going to have this little 2-dimensional slice of each of these vectors. So this is going to be four heads of 5 by 2. So each of these heads now has a different section of the original token, and each head has all of the tokens. And we're going to create our key tensor that's going to look pretty similar. The key tensor is the same, but here we've transposed once again to prepare it for the attention, because the inner dimensions have to match here. So we have T by HD, and the keys are HD by T. Okay, now we're going to multiply Q by K. And we're going to skip all of the kind of fine-grained stuff like scaling and masking. That's not important right now. We just want to watch where the data goes at each step. And so we'll notice that when we look at QK, this is 4 heads by 5 by 5. Each of these 2-dimensional slices of each token is multiplied against itself. And so each head computes its own little version of attention based on the slice of the dimension that it has. In this case, all of the slices were the same, but if they were different, you would see that each of these heads is performing a different level of computation. This is typically what happens. It's the motivation for multi-head attention, is that we want these different kind of routes of computation, like we're ensembling. Okay, let's create the values tensor. Oops. And for the sake of variety, this will look a little different, so we can actually distinguish between what happens at the very end. So these aren't going to be all copies of each other. We'll get this into the right shape. And here, of course, we also need to transpose. So we've got sequence length by head dimension, but we need to bring the head dimension out front, as we have for the others. So here are our values, and we have 4 computation heads, and each head has 5 dimensions corresponding to each of the tokens, and each have a slice. So remember, this was our first token, 1 through 8. And this head has the first 2 values of that token. This has the second 2 values, the third 2 values. And similarly for all of our other tokens. This is the last slice of our 5th token here. Okay, now it's time to multiply them all together and take a look. Because these values have different values, or rather the numbers in here aren't the same head to head as they are for the queries and keys. The query key attention scores are actually plucking out different amounts of these values. And so it's being multiplied across the values, and we end up with 4 heads. And each of these has performed its own version of attention. So this first head had this query key matrix, and this matrix was multiplied by this value tensor. And we end up with this. And so the different value tensors just allow us to see that each of these heads has done something different. But we're not done. So now we need to bring this head in here and swap the T with the H. So we're going to transpose again. And this is recombining the heads. This is actually the concatenation phase. So we end up concatenating the slices from each of the heads back into the original vectors where they came from. So you'll notice that this head 670, 700, and then this was the second part of the first token. And this was the third part of the first token. And this was the fourth part. We've recombined them all here. And so this just corresponds to our first token, and this is our second, and this is our third. And now we finally reshape this back into the original dimensionality, and we're back where we started. So we're just flattening these out. So this gets flattened out into an 8-dimensional tensor. And this is the same as taking these slices from each of the heads that we can trace back. So this first 2-dimensional slice came from the first head, this came from the second head, and we can follow it all the way back up the computation. And we can follow it all the way down, and we can see that, yes, when we get back here, we've actually just concatenated these different attention groupings, and they're back in their original form. And each of these tokens was able to get information from all of the other tokens across different attention heads. So this is my overkill explanation of multi-head attention, but it's very nice in that you can do this on your own. You can look through and basically in your head multiply each of these values so you can see what's happening at each and every stage. And basically you get to confirm that when we're splitting out the heads and reshaping them and transposing, it's working as promised.